So, for example, we have the vector space that we've been looking at, which is Rn, which is all these n-dimensional column vectors. And so we say that if you have vectors, say v1 up to vk, these are called linearly dependent if there exist scalars, real numbers, c1 up to ck. And this is the important thing, not all zero. If they're all zero, it doesn't count. Not all zero, such that when you compute the linear combination of the vectors, c1 v1 plus c2 v2 up to ck vk, you get the zero vector. So if there's a linear, if there exists one linear combination of the vectors with all of these coefficients, c1 up to ck, not all zero, and it gives you the zero vector, then the vectors are called linearly dependent. And a set of vectors is either dependent or independent. So the vectors v1 up to vk are linearly independent if they are not linearly dependent. And what this means is if c1 up to ck are scalars, and this linear combination is the zero vector, then all of the scalars have to be equal to zero. So this is what it means for vectors to be linearly dependent. And this is what it means for vectors to be linearly independent. So if you're given a set of vectors, how do you determine? So let's just take an example. Suppose we take v1 equal to 2, 3 in R2, and v2 equal to -1, 4 in R2. And the question is, are the vectors v1, v2 linearly dependent or independent? So you say, okay, well, suppose some linear combination, I'll call the scalars x1 and x2 instead of c1 and c2. Suppose x1 v1 plus x2 v2 is the zero vector, right? What does that mean? That means x1 times the vector 2, 3 plus x2 times the vector -1, 4 is the zero vector. What is this? This is the same as, if I do scalar multiplication, this is 2x1, 3x1 plus -x2, 4x2. All right. And if I add these vectors, I get 2x1 minus x2 and 3x1 plus 4x2. So what this says is that you have scalars x1 and x2 such that x1 v1 plus x2 v2 equals 0 only if this is a vector identity, right? Because x1 v1 plus x2 v2 is exactly this vector. And we ask, does it equal 0? Well, that's exactly the same as saying that this first coordinate is 0 and the second coordinate is 0. So what are the solutions of these two equations and two unknowns? Well, so you just use your high school algebra. If 2x1 minus x2 is 0, let me multiply by 4. 8x1 minus 4x2 equals 0. I add these equations, I get 11x1 equals 0. So x1 has to be 0. And if x1 is 0, x2 is 0. So by looking at these two equations and two unknowns, I solve them. And the only solution is x1 equals x2 equals 0. So let's come back to this. The only time x1 v1 plus x2 v2 is 0 is when x1 and x2 are 0. Therefore, the vectors 2, 3 and minus 1, 4 are linearly independent.
Wait, can you re-explain the algebra part you did when you got 2x1, when you got 8x1 minus 4x2 equals 0?
Oh, so I have these two equations, right? And then I'm just using whatever I want to use from high school algebra to solve two equations and two unknowns. I took the first equation and I multiplied it by 4. So that gave me 8x1 minus 4x2 equals 0. And then I added these two equations and the x2's cancel. I get 11x1 equals 0. So x1 is 0. And if x1 is 0, x2 is 0.
And because x1 equals 0 and x2 equals 0, that's what makes it linearly independent, right?
Yes,
okay.
That's the definition of linear independence.
And then if it was, for an example, if x1 was 2 and then x2 was 0, that would mean that it would be linearly dependent.
You are 100% correct.
Okay, thank you.
Sure. All right. Any other questions about? I'm just going to review really what I did this morning, go over more examples of putting a matrix in reduced row echelon form to solve a system of linear equations.
Professor, I just have one question in regards to the email, because you said the exam will cover lessons 1 through 11. Like, I want to know, like, in chapters, which sections of the book are...
You're talking about calculus, right?
No, I'm talking about this class.
No. Maybe I sent out the wrong email. For my calculus class, it covers lessons 1 to 11 in the syllabus.
Oh, it's because I got that email for some reason.
Oh, then I must have sent out
the same email.
Yeah, so I must have sent out the same email to both classes, and I thought I had changed it, but I'll go correct it and send out the revised email tomorrow.
Okay.
Yeah, because that doesn't make any sense for us. I'm very glad you asked, but yes.
Professor, I had a question.
Sure.
The day before the test, are you going to do like a mini review session during this office hours?
Yes.
Okay.
And I'll also make sure I'll have a review sheet, and I'll make sure I cover all the problems in a video that I post, because some students have conflicts and can't come to any of these Zoom sessions.
And the review sheet will be similar questions to the test.
Excuse me?
The review sheet will be similar questions to the test?
Yes, but they're supposed to cover everything. So the exam covers everything we've done up until the day before the exam. And if it happens there's something which is not exactly the same as a question on the review sheet, it's still something you're supposed to know. But I try to make the review problems as comprehensive as I can. And certainly if you can do all the kinds of problems on the review sheet, then you should do okay on the exam. Okay, so let's go forwards and backwards. So we have an m by n matrix, which is just a rectangular array of scalars. And it's arranged in m rows and n columns. So even your ordinary vector x1 to xm, let's say, in Rm, this is also a matrix. This is a matrix with m rows and one column, right? That's, or if you take 7, 0, 8, minus 2, minus 5, 11, this is a 2 by 3 matrix. 2 rows, 3 columns. And if I have another 2 by 3 matrix, I can add them. And just the way you add vectors by adding coordinate-wise, for matrices of the same shape, you can add them by adding coordinate-wise. So 7 plus 7 is 14, 0 minus 2 is minus 2, 8 minus 5 is 3, minus 2 plus 1 is minus 1, minus 5 plus 6 is 1, 11 plus 0 is 11. So for any shape matrix, if you have two matrices of the same shape, you add them by adding coordinates. And if you have a matrix, you can also do scalar multiplication. If you want to multiply this, for example, by the number 3, that just means you multiply every coordinate by 3. So 3 times 7 is 21, 3 times 0 is 0, 3 times 8 is 24. 3 times minus 2 is minus 6, 3 times minus 5 is minus 15, 3 times 11 is 33. So for matrices, just as for vectors, we have defined addition of matrices and scalar multiplication of matrices. Right? And matrices will come up a lot in this course, but right now we're looking at them just because there's a connection between solving a system of linear equations and certain operations on a matrix. So let me pick an example that will be in the notes. So when you're studying, it might be easier to follow. So, we're getting to the point in linear algebra where things are not necessarily so difficult, but you can't just solve it in one step. So here's a system of equations to solve. 2x1 minus x2 plus x3 equals 6. x1 minus 7x2 minus 4x3 equals 0. Minus 3x1 plus 2x2 minus x3 equals minus 1. So we have 3 equations and 3 variables. And we know using Gaussian elimination that there's a way to solve the system of equations by converting it to a simpler but equivalent system. Equivalent means a system with the same solutions. And there are 3 things we can do to a system of equations that give us equivalent systems. You can just interchange 2 equations. Like I could interchange equations 1 and 2. So now the second equation is the first equation, and the first equation is the second equation, and the third equation is still the third equation. So all I did to get from here to here is I interchanged. Right? I interchanged equations 1 and 2. Right? That's legit. Now, what we try to do with Gaussian elimination is get a variable with coefficient 1 in like the first equation, and then try to eliminate that variable for the next equations. So I'm allowed to add one multiple of a row to another. So let me go from here. I'm not going to change the first equation. And I'm not going to change the third equation. But I'm going to multiply the first equation by -2 and add it to the second equation. So when I multiply this first equation by -2, I get -2x1 and then plus 2x1, and that gives me 0 times x1. I've gotten rid of x1. -2 times this is 14x2 minus x2 is 13x2. -2 times this is 8x3 plus x3 is 9x3. -2 times 0 is 0, plus 6 is 6. So I got from here to here by adding -2 times the first row to the second row. And then the next thing I want to do is eliminate the x1 from the third equation. So what I'm going to do, I'm not going to touch the first equation. I'm not going to touch the second equation. But I'm going to multiply the first equation by 3 and add it to the third equation. And I do that because that eliminates the x1. Because when I multiply this equation by 3, I get 3x1 minus 3x1 is 0. Multiplied by 3, minus 21x2 plus 2 is minus 19x2. Minus 3 times minus 4 is 12. 12x3 minus x3 is 11x3. Let's see, is that right? Oh, sorry. No, that's right. I get, sorry, I'm multiplying this by 3. Minus 21. I'm multiplying this equation by 3. 3x1 minus, sorry, going from here to here. 3x1 minus 3x1 is 0. Minus 21x2 plus 2x2 is minus 9x2. Minus 12x3 minus x3 is minus 13x3 equals 0. So I eliminated x1. And now I look at the second row and I want to have the coefficient of x2 equal to 1. So I'm not going to do anything yet to the first equation or to this new second equation. But if I want the coefficient of x2 equal 1, I can multiply this equation by 1 over 13. And as I'm dividing by 13, that's x2 plus 9 over 13, x3 equals 0. Oops, I made a mistake. Back here, there was a 6. I forgot that 6. What happened to it? I just didn't copy it correctly. So this is 6 over 13. All right. Now here's the x2. I want to eliminate x2 from the first and the third equations. So my second equation, I like the way it is. My third equation for the moment, I like the way it is. I'm sorry, I keep forgetting to, just writing things down. This was 0, 6, minus 1. So this should have been a minus 1, and I don't know why I wrote down a 0. But what do I do to get rid of the minus 7x2? If I multiply the second equation by 7 and add to the first equation, that will kill this. So 0x1 plus x1 is still x1. 7x2 minus 7x2 is 0. 7 times this is 7 times 9. That's 63 over 13 minus 4. 4 is the same as 52 over 13. So that's 11 over 13. And I'm multiplying this by 7. This is 42 over 13 plus 0 is 42 over 13. So I've done 1, 2, 3, 4, 5 different steps, and I've got a new set of equations equivalent to the original set. And finally, I want this x2 to disappear. So I have the first equation is x1 plus 11 over 13 x3 is 42 over 13. x2 plus 9 over 13 x3 is 6 over x3. If I multiply the second equation by 19 and add it to the third, I'll get rid of the x2s. So 19x2 minus 19x2 is 0x2. And I have 9 times 19 over 13 minus 13. Let's see. Let me just do that little calculation so we can see what it is. I'm multiplying 9 by 19 over 13 and subtracting 13. And if I do that correctly, I believe that I will get 2 over 13 x3 equals, multiply this by 19 and add 6 over 13. And if the arithmetic that I've done is correct, I get 101 over 13. So let me do that out exactly, just so you see if the arithmetic is correct. So this is my set of equations that I got to without any problem. x1 plus 11 over 13 x3 is 42 over 13. x2 plus 9 over 13 x3 is 6 over 13. And minus 19x2 minus 13x3 is minus 1. So this is my first equation. It hasn't changed. This is my second equation. I multiply this equation by 19 and add. When I multiply this by 19, let me just do it here. If I multiply this equation by 19, I get 19x2 plus 19 times 9 over 13 x3 equals 42 over 13. And the third equation is minus 19x2 minus 13 x3 equals minus 1. And when I add 19 minus 19 is 0, I get 19 times 9 over 13. 19 times 9 is 171. 13 is 13 times 13 over 13. That's 169 over 13. So when I subtract, I have 171 over 13 minus 169 over 13, which is 2 over 13. That's what I got here, 2 over 13. And what about this calculation? I have 19 times 6 over 13 minus 1. What is 19 times 6? 6 nines are 54, 114. This is 114 over 13 minus 13 over 13. So that's 101 over 13. That's what I got here. So you do the arithmetic. This is, what you do in elementary school. But it's hard to do arithmetic correctly. And we have this. Now, what else comes next? Well, I'd like the coefficient of x3 to be 1. So what I'm doing is Gaussian elimination. x1 plus 11 over 13, x3 is 42 over 13. x2 plus 9 over 13, x3 is 6 over 13. I can get a 1 here by multiplying this equation by 13 over 2, and I get x3 is equal to 101 over 2. So I have this system of equations, and then I can eliminate x3 from the previous equation. So let's see. Suppose I subtract 11/13 times this equation from this equation. I get x1. Let's see, I'm not changing the other two equations yet. I multiply this equation by 11 over 13 and subtract. So I have 11 over 13 minus 11 over 13. And I have 42 over 13 minus 11 over 13 times 101 over 2. What is that? That's 42 over 13 minus, this is over 26. 101 times 11 is 1111. So this is 84 minus 1111 over 26. So if I manage to subtract 84 from 1111, I get 7, 2, 01. See, is that right? I think so. Yeah. Over 26. If I divide 13 into this, this goes in 91, 7, 1, 1. 9. Exactly. I mean, you just have to do this calculation by hand. That's what it is. It's just arithmetic. But when I do this subtraction, I get minus 79 over 2. And then finally, I eliminate the x3. So I have x1 equals minus 79 over 2. x3 is 101 over 2. Multiply this equation by 9 over 13 and subtract. I get x2 equals, and it's 6 over 13 minus this times 9 over 13. And lo and behold, what we get is the answer is minus 69 over 2. So this is the solution using Gaussian elimination. Okay. Now, it's always possible you don't like the solution, but it doesn't matter. That's what it is. Right? Any questions about this? I mean, this is just a lot of arithmetic. It's a calculation and there's no shortcut. You just have to do it.
And to prove that you got the right answer, you just need to plug in, right?
I'm sorry, it's kind of garbled. What did you say, please?
I said to confirm, like to check the answer, we just need to plug in, right?
Exactly. Exactly. Now, so this is Gaussian elimination, and I want to show how you do this using matrices. So this will be the Gaussian elimination side of the page. And now here I have matrices. So first of all, this is the system of equations we started with. So if you look at the coefficients of the variables, 2, minus 1, 1. That's the first row of a matrix. Second equation, 1 minus 7 minus 4. Third equation, minus 3, 2 minus 1. So this is the matrix of coefficients of the system of equations. But I also have the right-hand side, 6, 0, minus 1, and I add that column. So this is called the augmented matrix. The matrix, in a certain sense, that we're starting with is a 3 by 3 matrix of coefficients, and we augment or add to it by adding the right-hand column. Now, when we interchange two equations, what does that do for the matrix? Well, let me write down the matrix for this. It's 1 minus 7 minus 4, 0, 2 minus 1, 1, 6, minus 3, 2 minus 1, minus 1. And if you compare these matrices, what we did is interchanging equations here corresponds to interchanging rows here. We interchange rows 1 and 2. Now, how do we get from these equations to these equations? We multiplied the first row by minus 2 and added it to the second row. So in this system, what is the matrix? 1 minus 7 minus 4, 0. Same first row. Minus 3, 2, minus 1, minus 1. Same second row. But the new third row, the coefficients are 0 times x1, 13x2, 9x3, 6. And what we did was we multiplied to get from here to here. It's 2 times row 1 added to row 2. Multiplied this row by minus 2 times this row and added it to this. Okay. Let's see, what was the next thing we did? Here it is. So in our system of equations, we got from here to here. We didn't change the first equation or the second equation, but we multiplied the first equation by 3 and added it to the third. And what is our augmented matrix for this system of equations? If you look at the coefficients, 1 minus 7 minus 4, 0, 0, 13, 9, 6, 0 minus 19 minus 13 minus 1. So the first two rows are the same, but we got from here to here by multiplying row 1 by 3 and add to row 3. Right? What was the next thing we did? To get from here to here, I multiplied the second equation by 1 over 13. And the matrix for this system, 1 minus 7 minus 4, 0, 0, 1, 9 over 13, 6 over 13, 0 minus 19 minus 13 minus 1. So here I multiply one row, row 2, by a scalar, 1 over 13. If I multiply this row by 1 over 13, this is what I get. And you'll notice the three operations which you're allowed to perform on a system of equations correspond to what are called the three elementary row operations on a matrix. They are the following. You can interchange two rows. You can add a multiple of one row to a different row. And you can multiply a row by a scalar. Okay. How did I get from here to here? I eliminated the x2. I added 7 times the second row to the first row. What does the matrix look like? 1, 0, 11 over 13, 42 over 13, 0, 1, 9 over 13, 6 over 13, 0 minus 19 minus 13 minus 1. How did I get from this matrix to this matrix? I multiplied the second row by 7 and added to the first row. So 7 times the second row added to the first row gave me a new first row. What is the matrix here? 1, 0, 11 over 13, 42 over 13. That hasn't changed. 0, 1, 9 over 13, 6 over 13. That hasn't changed. But the new third row is 0, 0, 2 over 13, 101 over 13. And I got that by adding 19 times the second row to the first row. And that eliminated the x2. What was the next thing I did? I multiplied the third row by 13 over 2 to have x3, to give x3 the coefficient 1. The matrix is 1, 0, 11 over 13, 42 over 13, 0, 1, 9 over 13, 6 over 13. And when I multiplied this row by 13 over 2, I get 0, 0, 1, 101 over 2. And then step by step, I'm going to make each of these two numbers 0. So here's the second row, I'm not changing it. Here's the third row, I'm not changing it. But if I multiply the third row by 11 over 13, or by minus 11 over 13, and add to the first row, I get 1, 0, 0. And I did the calculation, it was minus 79 over 2. And then the last step is to multiply the third row by minus 9 over 13 and add to the second row. And when I do that, I get 1, 0, 0, minus 79 over 2, 0, 1, 0, 9 over 13, 0, 0, 1, 101 over 2. And if I translate this back into equations, this first line is the equation x1 equals minus 79 over 2. The second line is the equation x2 is minus, oops, what happened? I just copied this down wrong, I guess. Minus 79 over 2, 6 over 13. No. Sorry, minus 69 over 2 and 101 over 2. And that corresponds exactly to these three equations. So what are called elementary row operations on a matrix. What are they? Interchange two rows, any two that you feel like. Multiply a row by a non-zero number, okay? And add a multiple of one row to a different row. And that sequence of elementary row operations led me to this matrix. Now, if you look at this matrix, it has very nice property. First of all, in each row, the first non-zero number is a 1. Second, as you go from one row to the next, the ones are moving to the right. First column, second column, third column. Finally, in every row where there's a leading, the first term is a 1, in that column, everything else is 0. 0, 0, 0, 0, 0, 0. And a matrix in this form is said to be in reduced row echelon form.
Professor, can you move the paper up? Yeah, I couldn't see the last row. Sorry.
Right. So this is called reduced row echelon form. And this is exactly the kind of form we would love to put a matrix in order to solve a system of equations. Because this allows you to read off the solution very easily. But to get facility with this, to be able to do it, you really need to solve a lot of problems. So let me do, and these problems take time. Well, that's just the way it is. So the important theorem says that by elementary row operations, you can always put a matrix into reduced row echelon form. And there's a proof of that, or there will be a proof of that in the notes. But let me just use this to solve a system of equations. So here's a system of equations. 6x minus 5 equals minus 3. 7x minus 2y equals 6. 8x minus 3y equals 15. So we have three equations and two variables. So what is the augmented matrix? So the matrix of coefficients is 6 minus 5, 7 minus 2, 8 minus 3. It's a 3 by 2 matrix. And when we add the right-hand side, you get minus 3, 6, 15. So I want to put this in reduced row echelon form. And it's not like there's only one way to go about doing that. You pick a way that you like. So, for example, I could, if I wanted a 1 here, I could multiply this by 1/6. But since I prefer to avoid fractions if I can, let me start by interchanging the first two rows. 7 minus 2, 6. 6 minus 5 minus 3. 8 minus 3, 15.
Wait, I have a question. Does it matter that there's no y by the minus 5? Or
Oh yeah, I forgot to write it. Sorry. Sorry, that y, I don't know where that y came from. The equations I wanted to write down were 6x minus y equals minus 3. So this should be a minus 1. 6x minus y equals minus 3, 7x minus 2y equals 6, 8x minus 3y equals 15. So the augmented matrix is 6 minus 1 minus 3, 7 minus 2, 6, 8 minus 3, 15. So I'm going to interchange these rows. So I have 7 minus 2, 6, 6 minus 1 minus 3, 8 minus 3, 15. Then I leave the second row and the third row alone for the moment. But I take the first row and I subtract the second row. So that's the first row plus minus 1 times the second row. So 7 minus 6 is 1, minus 2 plus 1 is minus 1, 6 minus minus 3 is 9. So I took the first row minus the second row. And then 1 minus 1, 9, 8 minus 3, 15. I'm going to take I want to get a 0 here. So if I take minus 6 times the first row and add to the second, I get minus 6 plus 6 is 0. Minus 6 times minus 1 is plus 6. 6 minus 1 is 5. Minus 6 is minus 54. Minus 3 is minus 57. And then I want to get a 0 here. So I multiply the first row by minus 8 and add. Minus 8 plus 8 is 0. Minus 8 times minus 1 is 8. 8 minus 3 is 5. Minus 8 times 9 is minus 72. Minus 72 plus 15 is minus 57. Okay, good. The first row is 1 minus 1, 9. The second row is 0, 5 minus 57. If I want to make things simple, take the second row and subtract it from the third. I get 0, 0, 0. Matrix is just getting simpler. Then I want a 1 here. So 1 minus 1, 9, 0, 0, 0. Divide this row by 5. I get 0, 1 minus 57 over 5. And I want a 1 here. So I add the second row to the first row. 0 plus 1 is 1. 1 minus 1 is 0. Minus 57 over 5 times 9. 9 is 45 over 5. 45 minus 57 is minus 12. And now this matrix is in reduced row echelon form. All the zero rows are at the bottom. And on the rows with the non-zero element, the first non-zero number in each row, as you go from left to right, is a 1. The ones move to the right. What does this say as an equation? It says x equals minus 12 over 5, y equals minus 57 over 5. We solved the equations. Maybe we should check. The first equation, 6x minus y, that's 6 times minus 12 over 5 minus 57 over 5. That's minus 72 over 5 plus 57 over 5. That's minus 15 over 5, or minus 3. That was the first equation, minus 3. The second equation, 7x minus 2y. That's 7 times minus 12 over 5 minus 2 times minus 57 over 5. Let's see. 7 times 12 is 84, minus 84 over 5. 2 times 57 is 114 over 5. 114 minus 84, that's 30 over 5, or 6. That's what it's supposed to be. And if you plug into the third equation, you should also get the right answer, 15. So here we solved a system of equations.
Professor,
Yes,
how do we get the 1 minus 1 and 9?
here
Yeah,
I took the first equation and I added minus 1 times the second equation to it. Or in other words, I took the first equation minus the second. 7 minus 6 is 1. Minus 2 minus minus 1, that's minus 2 plus 1 is minus 1. 6 minus minus 3 is 6 plus 3 is 9. Right? You're allowed to add a multiple of one row to another. So I took the second row, multiplied it by minus 1, and added it to the first row.
all right, thank you.
Professor,
Yes,
question. Okay, so when doing matrices, your goal is to get the bottom row to equal 0, or
no, your
No.
goal is the following. So it depends on the problem, of course, but a typical problem is given a matrix A, use the 3 elementary row operations to obtain a matrix B that is in reduced row echelon form. That means in every row, the first time there's a non-zero element, it's a 1. And in the next row, the first non-zero element is a 1, but it's to the right of the column where the first one is. So as you move across, the first non-zero element is always a 1. As you go from one line to the next, the ones are moving to the right. Any row which is all 0, there could be a lot of them, is at the bottom. And whenever you have a 1 as the first non-zero entry in a row, in that column, everything else is 0. So all of those conditions must be satisfied for your matrix to be in reduced row echelon form. And it can always be done, but it might take a lot of work.
When doing the Gaussian elimination, so we can pick whether we want to do it with the matrices or the other way, right?
So it depends what the problem is. If the problem says solve this system of equations, then you can solve it any way you like. If the problem says use Gaussian elimination, then that's what you're supposed to do. If it says solve the system of equations by putting the augmented matrix in reduced row echelon form, that's what you have to do.
Oh,
Or you
okay.
might have a problem that just says put this matrix in a reduced row echelon form. So for example, suppose I give you the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. And you have to put this in reduced row echelon form. So that's what you do. There's no more equations. It's just using the matrix. So for example, you already have a 1 as the first non-zero number in the first row. You want a 0 everywhere underneath that. So you could take the second row minus 4 times the first row. 4 minus 4 is 0. 5 minus 8 is minus 3. 6 minus 12 is minus 6. Then you want a 0 here. So you take the third row minus 7 times the first row. 7 minus 7 is 0. 8 minus 14 is minus 6. 9 minus 13 is minus 12. Then you want this to be a 1. So I could multiply this row by minus a third. I get 0, 1, 2. Then I want this to be a 0. So I subtract twice the second row from the first row. 1 minus 0, 2 minus 2, 3 minus 4 is minus 1. And then I want a 0 here. So I multiply this row by 6 and add, and I get 0, 0, 0. And now I'm done, because this matrix is in reduced row echelon form. In the first row, I have a 1 as the first non-zero element, and everything else in that column is 0. In the second row, I have a 1 as the first non-zero element. It's to the right column of this, and everything else in this column is 0. And the third row is all 0. So this is the result.
In the exam, we have to do it both ways, right?
Excuse me?
In the exam, we have to do it both ways, right?
Well, there will be questions, yes, using each method.
Okay.
Up to a point. You have to understand, it's a 2-hour exam, so some of these questions can take 15 minutes. And I can't give you 10 questions that take 15 minutes in a 2-hour exam. Right?
Right.
And until I make up the exam, which I haven't done yet, I won't know what's on the exam. But in any case, I'm not going to tell you. So you're supposed to know everything. All right. But the exam's almost a week away, which in summer school language means almost a month. So, but it is next Wednesday. All right. Okay. Any more questions about anything that I can help you with?
Wait, I'm sorry. You did 6 times the second row, and then you added that to
Yes.
the third row. Okay.
That's how I got 0, 0, 0 in the third row.
Okay. I think I'm gonna hate this. I had a question on, well, it's kind of what we did before. It was on the homework 3 for 1D. I like solved it, but when I checked, I solved for W, and when I checked to plug it in, it wasn't working.
Which problem was it?
I'm sorry, 1D from on page 40, either 42 or 43. I don't know.
Let me see if I can find it.
44.
I'm sorry, thank you, 44. Yeah, I was like, I think I did this right, but it wasn't working, so I'm sad.
So which section is this in?
1 point,
1.5.
thank you.
And which problem was it?
1D.
1E.
No, D as in dog.
Oh, where you have 3 equations and 4 variables?
Yes.
So and you use Gaussian elimination
Yes.
and you didn't find an answer you liked.
No.
It's 5 variables, not 4.
No,
Sorry?
for 1D is only 4 variables.
Right, but let's see. So,
Wait, isn't there 5 variables there?
There's 5 in E.
yeah. So in section 1.5, exercise 1D. So is this it? 2x minus 4y plus 6z plus 10w equals 0. 2x minus 3y plus 9z plus 21w equals 0. X minus y plus 8z plus 9w equals 0. Okay, well, again, they're always, I mean, for example, I'd like to have a 1 up here. So I can either interchange rows 1 and 3, or I can just multiply this equation by a half because everything's even. So if I multiply this by a half, I get x minus 2y plus 3z plus 5w equals 0. 2x minus 3y plus 9z plus 21w equals 0. And x minus y plus 8z plus 9w equals 0. Right? Is that okay?
Yeah.
And then let's see. So here I have x minus 2y plus 3z plus 5w equals 0. If I subtract twice the first equation from the second, I get 2x minus 2x is 0. Minus 3y plus 4y is y. 9z minus 6z is 3z. 21w minus 10w is 11w. Right? Is that okay?
Yeah.
And let me just do 2 steps at once. Let me also subtract the first equation from the third equation. So x minus x is 0. Minus y minus 2y is minus y plus 2y is y. 8 minus 3 is 5z. And 9w minus 5w is 4w. Right? So I seem to get that. Is that okay?
Yeah.
Right. So then I want to get rid of this 2y here, so I can take twice the second equation and subtract it from the first. So here's my second equation. Y plus 3z plus 11w equals 0. If I multiply this equation by 2 and add it to the first equation, I get 0 plus x is x. 2y minus 2y is 0. 6z plus 3z is 9z. 22w plus 5w is 27w equals 0. And again, if I take the third equation and subtract the second, the y's cancel, and I get 5z minus 3z is 2z. 4 minus 11 is minus 7w equals 0. Right? So it looks like that's what I get. Okay?
Yeah.
And then, again, I just don't want to, I want to get a z here, so let me just divide this by 2. So if I divide it by 2, I get z minus 7 halves w. It's just a little bit quicker. Okay?
Mhm.
And then I want to get zeros here and here. So if I take the third row, multiply it by minus 9 and add to this, or in other words, if I take this minus 9 times this, what do I get? So my third row, which I like, is z minus 7 halves w equals 0. If I take this minus 9 times this, I have x minus 0. 9z minus 9z is 0. I have 27 minus 9 times this. That's 27 minus 63 over 2. 27 is the same as 54 over 2, so 54 minus 63. If I'm lucky, that's minus 9/2. W equals 0.
Okay, this is why I messed up. I think I added the 50. I added 54 and 63 because I thought that when I took away the x.
Oh, sorry. No, I think you're right and I'm wrong. I'm multiplying this by minus 9 and adding. So minus 9 times minus 7, that's plus 63 over 2. And 27 is 54 over 2. So when I add them, I get 117 over 2.
Yeah.
So this is 117 over 2. Right? It's minus 9 times this row plus this. And then I want to get rid of the 3, so I multiply this by minus 3 and add. So I have y, 3 minus 3 is 0. Minus 3 times this is plus 21 over 2, plus 11, which is 22 over 2. So this looks like it's 43 over 2 times w equals 0. So if any of this is correct, I won't know until I'm done and I check. This says that for any w, x is equal to minus 117 over 2 times w. Y is minus 43 over 2 times w. Z is 7/2 times w. And w is just w. So if I write this as a vector, the vector x, y, z is this vector, which is minus 117 over 2, minus 43 over 2, 7 over 2, 1, all times w. So if we're lucky and we plug this into these equations, that's the answer. But, you know, who knows? Yes, all it is just, it's just arithmetic. And it's just a matter of doing the calculations as carefully as you can, checking. And if it doesn't work, then you just go see where you made a mistake. And eventually you'll get the answer.
Oh, I think I had multiplied the 11 by 3 instead of trying to get it with the denominator of 2. And that's where I made my error.
Okay, whatever. You know, I mean, it's impossible to do this kind of math without making a lot of mistakes. You just have to go back and check and double check and see what's going on.
Thank you.
Okay. All right. That's it for today. I'll be back on Monday.
Thank you, Professor.
All right.
Thank you, Professor.
Have a good weekend.